So this video is about radians. We're going to find out what exactly a radian is. Now, a circle, very familiar. There's not a lot about circles that you can notice. One of the things you can notice is the width of a circle from one side to another. As you know, this is called the diameter. Let me write that in. And then, of course, there's the distance all the way around, the circumference. And interesting, obviously the circumference is larger than the diameter, but how many times larger than the diameter? If we take this diameter length and attempt to fit that diameter around the circumference, obviously one's not enough. Let's try it again. There we go. That's two lots of this diameter length. It's still room. I'll take a third one. Interesting. There's a gap. 3 diameter lengths. There's one diameter length, followed by another diameter length, followed by a third diameter length. So we're wrapping diameter lengths around the circumference to discover that they almost 3 times, almost 3 diameters fit round the circumference, but not quite. There's a little gap. So the circumference of a circle, there's circumference, is 3 and a bit lots of the diameter. That's a very lengthy way of saying that the circumference is 3 and a bit, just a bit more than 3. That's the number pi, and the diameter. 3 and a bit lots of the diameter. That's what the circumference is made up, and that's a very familiar formula. The C equals pi times d. This is where pi comes from. How many diameters fit around the circumference? 3 and a bit. Pi. Pi, very, very interesting number. 3.14159, and it goes on and on and on and on. It never finishes. There's no repetition. There's no pattern in the digits. It doesn't stop. It's what's called an irrational number. That's a different story. So C equals pi times d. 3 and a bit lots of the diameter fit around the circumference. Now, if we half the diameter, let's draw another picture. If we half the diameter, of course, we get the radius of this circle. And if we half the circumference, we get a semicircle. Now, if the diameter fitted just over 3 times round the circumference, then the radius will fit just over 3 times around a semicircle. We've halved both the lengths. Circumference has been halved, and the diameter has been halved. So the radius will fit 3 and a bit times around a semicircle. Now, interesting things happen if we join up the ends of this arc that's the same length as the radius length. Let's just put that down. And radius length again. And the third one, radius length. And then there's just that little bit of a gap left. That's just the way the circle is. And join this up to the center. Now, we've got a natural size of an angle here. It's not the normal way of describing this half-turn angle as 180 degrees, dividing up this angle into 180 little bits. 180 is a rather strange number. Could have been 200. But here's a very natural occurring division of this 180 degree angle, where we take a radius and lay the radius along the circumference. And here, this angle here, this is what 1 radian is. So there's another 1 radian here, and there's another 1 radian here. So we've got 3 radians and a bit of a radian. So we have pi radians making up a 180 degree angle, this half turn angle that's at the center of this semicircle. So radius, 1, 2, 3 and a bit radius lengths fit around this semicircle because 3 and a bit lengths of this diameter fit around the circumference. That's old familiar knowledge. So we lay out the radius length along here, we get 1 radian at the center. We lay out another radius length here, we get 1 radian at the center. We lay out another radius length, we get 1 radian at the center. And there's that little bit, that's 0.14159 and so on, left over. So just over 3 radians make up 180 degrees. So 180 degree angle is the same as pi radians. So there is a radian, and there is a conversion. 180 degrees pi radians. So I think what we should do at this stage is let's just get rid of all this writing. Let's move on to a different diagram. Let's just recall what we've done. 1 radius fits along there to give you 1 radian angle. So that's a radius, that's the same length as that radius, there's 1 radian. And because of the nature of the circle and pi, we know that 3 and a bit radius lengths fit into this semicircle. So we get just over 3 radians making up a 180 degree angle. So let's put one column with degrees and one column with radians. And what we've discovered, 180 degrees pi radians. Now usually when we write an angle down in radians, we don't need to write rad or r or anything like that. We just write the number down. So there's the number 3.141, etc. So we just write that down with no unit after. It's understood it's radians. 180 degrees, we always need this little degree sign to show that we're measuring an angle in degrees. So that's the basic conversion. And then once we've got this, of course, we can use this basic fact to do all sorts of other conversions. Like if we double 180 to get 360 degrees, we double this to get 2 pi radians. If we half 180 degrees, we get 90 degrees. And halving pi radians, pi upon 2. That's how you'd describe this. Pi upon 2, pi divided by 2. So pi divided by 2 radians, pi upon 2 radians is 90 degrees. Now, we can also divide this by 4, or this by 2, which is the same thing, to get 45 degrees. Dividing this by 4, pi upon 4, or dividing this by 2, a half of pi upon 2 is pi upon 4, okay? So half of 90 gives you 45. So 45 degrees pi upon 4 radians. We could divide this by 3 to get 60 degrees, which would be equivalent to pi upon 3 radians. We could divide this by 6 to get 30, which would be equivalent to pi upon 6 radians. Or we can half that to get 30, and we can half this to get pi upon 6. A half of pi upon 3, 1 times pi is pi, 2 pi times 3 is 6. So a half of pi upon 3 is pi upon 6. So there's a whole load of equivalents, and obviously no degrees, no radians. Or 0 radians, I shouldn't say no radians, there's 0 of them. So there's a whole load of equivalents. And so familiar diagrams like this equilateral triangle, where we'd normally put 60 degrees, 60 degrees, 60 degrees, if we measure in radians, we would just replace 60 degrees by pi upon 3. So there's your familiar equilateral triangle. There's also the familiar square diagram where we have 90 degrees. So this would be pi upon 2, pi upon 2, pi upon 2, and pi upon 2 if you're measuring in radians. Let's half this. So a half of pi upon 2 is pi upon 4. Half of 90 degrees is 45 degrees. So measuring this, there's your pi upon 2 radians. Half of the pi upon 2 would give you pi upon 4 radians. So there's pi upon 4, and there's pi upon 4.